here. So yeah, good turnout today. There's quite a few people on Zoom or Teams, hopefully you can hear us. Let us know if you can. So today we're hosting Ken Harris from UCL. Thank you very much for coming. So Ken has quite an interesting background. He did maths at Cambridge before doing a robotics PhD, and then working at Rutgers, if I remember correctly, and so a postdoc career, and now he's a professor of quantum science at UCL. So today we're going to hear a little bit about statistics in neuroscience and neurodevelopment. Yeah, take it away. Thanks very much.
Thank you. Thanks. So thanks so much for the invite. Sasha asked me what I wanted to talk about, and this is what I want to talk about. It might not be what you want to hear. Maybe it's something that's useful. Nevertheless, if you haven't thought about this, it's really something you've got to take into account, because the truth is that a lot of the stuff that has been published in neuroscience and continues to be published in neuroscience uses incorrect statistics, which means you can draw an invalid conclusion. And if you have a statistical method that is invalid, you can really prove anything at all. So we've really got to get this right. All right, so nonsense correlations. What was the button? Oh, there we go.
Yeah.
Is that right?
Yeah, that's great.
I'll figure it out. Okay, nonsense correlations and how to avoid them. All right, so what is a nonsense correlation? So this is the paper. This isn't what, oh, it's the wrong button. But you don't point it, you got to point it at an angle. It takes getting used to. I think I'm not going to bother. This is the paper that introduced the term, and it was tongue-in-cheek from the beginning. Mr. G. Udney Ewell at the Royal Statistical Society in 1925 presented a graph that showed two things. The first is standardized mortality rates, the rate of death, and the second is the rate of marriages within the Church of England. And notice that these two were perfectly correlated over the course of the late 19th century. So of course, you know, we don't think there's a causal relation between them in either direction. But more than that, we don't even think there's really a correlation between them. But they are amazingly correlated. And if you do a Pearson correlation, you'll get an incredibly significant result. So this is a nonsense correlation. It's only there because you've got two things that are changing slowly with time, right? And if you've got two things that are changing slowly with time, they're either going up or down. And that means they're either going to be positively correlated or negatively correlated. So you're going to get a correlation one way or another, but it could be just chance. So what I'm going to talk about today is how this can happen in neuroscience, because it really can, and what you can do about it so that you're actually drawing genuine conclusions about your data rather than finding these nonsense correlations. All right, so a nonsense correlation, if you've got two variables that both depend smoothly on time, they're correlated with each other, but only because of time dependence. How do we correct for the common time dependence? And what do we do if the variables are vectors or spike trains, decisions, etc.? You can use this to prove causality, some of these tests, the randomization tests, but that's not the point. The point is just about finding a genuine correlation that's generally statistically significant. We'll worry about causality some of the time. All right, so here's an example of it's synthetic data, and most of what I'm going to show is going to be synthetic data, but you get it with real data too. An example of a nonsense correlation. So suppose we recorded 10 neurons, and what we have here is the firing rates of these neurons. Every one of these 10 curves is meant to represent the firing rate of a neuron over some period of time, some large time bins. And the reason I'm showing simulated data is because then with the simulated data, you can know whether your null hypothesis is true or false. And in this case, we know that the null is true. So we've got these 10 simulated neurons, and their firing rate is a random walk that drifts up and down purely at random, independently for each one. And the target variable, what we're trying to do is we're trying to predict from the firing of those neurons, we're trying to predict a variable that changes in these blocks. So what inspired this was the International Brain Lab task, where there's a stimulus on the left or right, and the probability switches in blocks. I was part of the team working on that, and this was something we needed to test statistically. Is does the brain encode the block on the left or right? The other thing about this is it doesn't move with your hand.
I have no answer for that. I'm very sorry.
Yeah.
It only works if you try it at the screen.
Okay. Yeah. All right. So the question is, can we predict this this block variable from these neurons? And they're completely independent, and I know they are because I programmed them, right? So this is a random block, and these are random independent neurons. And what you have in orange is predicting the block by linear regression. And it does pretty good, right? It's not perfect, but it does pretty well. And if you do a Pearson correlation or any statistical test, if you do a generalized linear model, any of that stuff, you'll get a very, very significant result, even though there's absolutely no relationship between these neurons and this block, or this target. So that is a nonsense correlation. We predicted B from A with very high statistical significance, even though they were completely independent. All right, how might you think to solve it? I'm going to start by going through a whole lot of things that don't work. So you might think, oh, well, we'll solve it with cross-validation.
I know the containers of that.
Sorry, the speaker is muted.
Good? Can you hear me?
So.
Can you hear me online?
On Teams, can we hear you?
Yeah.
Okay, good.
Everybody,
all right.
Please mute yourselves now.
All right. So, yeah. So can we predict the block from the training set and evaluate it on the test set? So in orange, we see the prediction on the test set, right? And you see that it's pretty much following the same trend because these neurons are slowly drifting. Of course it is, right? The neurons haven't really changed their rate much since the previous time step. So the prediction is pretty same as the previous time set. So the prediction on the test set is pretty good. And if we evaluate it with the cross-validated predictability, it's way above 0, right? So we're getting a good score on cross-validation. this is taking a random set of trials to be the test set. Maybe it'll be better if we don't take a random set of trials, but we take a continuous set of trials, because then we don't have this neighboring continuity thing. And that helps a bit, but it's still predicting this way better than 0 on average. So cross-validation hasn't solved the problem. We don't really have a correlation between the neurons and the block variable. But when we learn to predict the block variable by cross-validation, and we evaluate it on a separate test set, we still get a good prediction, even though there's no real correlation. All right, so it's a nonsense correlation. So what might work? There are lots of other things that don't work, and I'm not going to talk about those. But what might work, we need to revisit the basics of statistical theory, randomization and permutation tests, and stationarity. And everything I say here is going to be about classical statistics of the sort invented by Sir Ronald Fisher. You can do Bayesian statistics or other things. I think all of this still applies to that, but we'll just deal with the simple case. Oh, and there's a paper, now 5 years old, nearly 5 years old, preprint, which I might put in a journal, but maybe not, which describes this. Okay, so let's start by going back to the basics, the t-test, right? So the t-test is your classical statistical test. You've got two populations, X and Y, and they're independently drawn from a Gaussian distribution. You don't know the mean or the variance, but you want to test, do they have an equal mean? If this null hypothesis is true, then the t statistic follows a t distribution, and you can test whether you get an extreme value of the t distribution to test your null hypothesis. There's a massive assumption here, which is this word, independent. It requires X and Y to be independent, not just of each other, but across different trials. So if trial 2 is correlated with trial 3, this is not valid. And that's the problem in the slowly varying time series we had. Because things change slowly with time, the successive time points aren't independent, and the assumptions of your standard statistical tests are invalid. So you reject the null hypothesis, but just because of this incorrect assumption. So the problem is, first, simultaneously recorded neurons aren't independent. Second, successive trials in an experiment aren't independent. And if you assume they are, you can reject the null hypothesis for this reason alone, and your study is worthless. I'm not going to believe that you found an effect if it could just be a statistical artifact because you assumed this independence. And you know, I've published a lot of papers back in the day which did this because we just didn't think about it. We just didn't think about it. But you can get p-value of 10 to the minus 12 when you've got no effect by ignoring this independence assumption. Okay, so what's the solution? The solution is also about 100 years old. The best solution is still the one that's 100 years ago old, and that is the randomization test. So this is what you have to do in a clinical trial. You absolutely have to do it. You won't get your drug approved if you don't do a randomized experiment. So the classical randomization test, you divide the population into two groups, control or treatment. You measure a test statistic, which is any measure of difference between the groups. It could be t, it could be something else. And the null hypothesis is that the treatments have identical effects. And the way you test your statistic is you compute your test statistic, and then you make a null ensemble by regenerating the randomization of the subjects into the control and treatment group 999 times, and you get your p-value as the rank of the actual test statistic within the 1,000 values of the actual one plus the 999 randomizations. So the p-value is somewhere between 0.001 and 1, and it satisfies this formula, the probability that getting a p less than or equal to alpha is less than or equal to alpha. That's what you need to have a valid p-value. All right, and that's what a randomization test does, and they're almost foolproof. There are all sorts of ways you can go wrong in statistics, but a randomization test, if you do a randomized experiment and a randomization test, the only way you can go wrong is if you do something stupid, like a programming bug or something like that. It doesn't make any assumptions other than that you randomize your data. In fact, the history of the t-test is that Fisher always wanted to do a randomization test, but computers weren't good enough. Well, they didn't exist. They had these hand-cranked desktop calculators that they used. So there's no way you could do this randomization test where you re-randomized your variables and reassign them. The t-test was an approximation to the randomization test because it was all you could do in those days. All right, so the first lesson is randomize everything that is not nailed down. When you do your experiment, anything you can think of to randomize, do. I'm going to show an example later of a collaboration with Andy Peters, where Andy showed some stimuli of different with different trial intervals. Luckily, those were randomized. We didn't think at the time that we were going to need that randomized times, but it turns out that it was really useful to do a randomization test. So randomize everything that's not nailed down, the stimuli, manipulations, rewards, context, everything you can think of. So if you've got a reward for getting it right, don't just give a reward for getting it right, give 80% chance of a reward for getting it right and 20% chance of getting it wrong, or something like that, because then you can test, is there a significant and actually causal effect of the reward? All right, so let's get on to more details of how you would do this. So just to revisit a bit of probability theory, a random process is a probability distribution over the space of histories of the measured variable. So a probability distribution, something like a Gaussian distribution, is a random variable, defines a random variable, which is one number. A random process is a probability distribution over a history. So the point is, we've got the set of all possible histories, all things that might have happened in the experiment, all histories of the neurons firing, of the behavior that the mouse made, all that sort of stuff. And we collect them all together into a set of histories, and the random process gives each one of those a number, just the probability of this history to happen. So that's a random process. It's a probability distribution over histories. And even if successive time points are not independent, even if you have this slow drift, there's still a random process that goes on behind the scenes. We don't know what the probability distribution is, but we can say things about it. So for example, if you do a population recording, then you denote the firing rate of neuron N of your population on trial T as XNT, and you get a big matrix of number of neurons by number of time points. And this gives you a big vector summarizing the firing rate of all cells at all times. The behavioral state at trial T is YT, and then we get a vector, I don't know what happened here, a vector of the Ys at every time. So we got two big vectors. They define the history of the neuron activity and the behavior throughout our experiment. And the data of the recording is this pair of vectors, right? And what we want to do is we want to make an inference about the probability distribution from this single observation. We only observe one history of our experiment because that's all that happened. But we can still say something about the probability distribution it came from, and that's how we're going to design our statistical test. So a null hypothesis is a statement about this probability distribution that governs the neurons and the behavior. It doesn't need to be a complete formula. There's no way we can write down a formula, but we can say something. So let's suppose that what we're saying is that the neurons are independent of the block variable. In that first example, where we've got the stimuli coming in blocks on the right or on the left, the choice is coming to the right or to the left, we're saying that the history of the neurons is independent of the history of that block variable. That means that different neurons can still be correlated with each other and across different times, right? So neuron 1 and 2 might be correlated at the same time, and neuron 1 at a particular time might be correlated with the same neuron a bit into the future. And also the block variable can be correlated, and it certainly is because it normally doesn't change. But the null hypothesis is that the sequence of neural activity is independent of the sequence of behavioral variables or of the block variables, right? So at any neuron, at any time, is independent of the behavior at any other time. So this now gives us a null hypothesis we can test, right? So the thing is, before we were making this independence assumption that the activity of the neurons was independent across trials, that was a bad approximation to make because it's just not true, and we reject our null hypothesis for that reason alone. What we're really interested in is the neurons being independent of the stimulus, which comes in these blocks, even though they're not independent of each other. And this is the null hypothesis we want, that the whole history of the neurons is independent from the whole history of the stimuli. All right, so how are we going to test that? So we can use the randomization test that we talked about before. So if X is the firing rate of the cells on all the trials, and Y is the stimulus block for all the trials, we want to test if the sequence of X, the history of X, the history of neural activity is independent of the history of the block variables. And this is a randomization test, but I think it's worth giving it its own name, which is a pseudo session method, right? So if Y is the stimulus, we generated Y, and we know what its probability distribution is because we generated it. So the way you use a randomization test is you say, can you predict the actual stimulus history better than a randomly regenerated stimulus history, right? We can predict them because we have a nonsense correlation like we saw at the beginning. There's a nonsense correlation. You can predict the block from the neurons. But you can also predict a random block from the neurons. And the question is, can you predict the actual block history better than a random block history from the neurons that you record? And so this is what we do. We have a test statistic that measures how well you can predict the stimulus history from the firing history. It could be anything. We'll use least squares error here. And you compute that for the actual data, and then you re-randomize the block sequence according to the original distribution that you sampled it from. You get your null distribution. You have 999 of these null values, and you look where the actual test statistic lies within the null ensemble. So let's look at it in action. So here we have the case where we've got these random neurons and a random block variable, and you can predict it pretty well, even though they're independent. But here's the thing, if you have a different random block variable, you can predict that pretty well as well. And in blue here, you see the null distribution, like the 999 randomly sampled blocks, and this is how well you can predict them. And in orange, we have the actual block, which is right in the middle. There's nothing special about it. Yes, you can predict it, but you can predict all the random ones too. And in fact, because I simulated this, I know that this just is a random one that comes from the same distribution as all the other random ones. So the thing is, we've found a test now that isn't subject to nonsense correlations. Because yes, these are autocorrelated. Yes, this is autocorrelated. Yes, we can actually predict it pretty well, but we can predict a completely random one just as well. So we haven't rejected the null hypothesis, and that's good because the null hypothesis is actually true. If there actually was an encoding of the stimulus, which is what we see here, you can see that when the stimulus comes on, it's shifting the neurons. Now you can predict this better than that, right? And now the test statistic, which is the squared error, is substantially lower. This thing has a mind of its own. Substantially lower for the actual stimulus than for the null distribution. So in this case, we will reject the null hypothesis. In this case, we won't. So what we've got is a statistical test here that's not subject to nonsense correlations. When there isn't a genuine effect, it doesn't reject the null. When there is, it does. And the important thing is that when we regenerate the block sequence, we have to regenerate it exactly the same way that the original data was generated, right? So it looks the same, you know, it's got the blocks of the same length, it starts in the same condition, etc. All right, so by the way, I should say, if anyone has any questions or yes?
Sometimes people, instead of generating new random variable, they're like circularly commute the new variable.
Okay. Okay, I said at the beginning, there are lots of things that don't work that I weren't going to talk about. That's one of them. It almost works. It's not bad. The circular permutation is a lot better than just doing a classical statistical test, but it can go wrong. The reason is that if you think about these neurons, you know, they're drifting slowly. That means where they start could be quite different to where they end up, right? And now if you circularly permute it, you've got a sudden, whoa, what just happened? You've got a sudden jump in the firing of the neuron. And for some test statistics, that will give you a high value of the test statistic. So you can reject the null hypothesis because your circularly permuted data doesn't look like the original data, right? Because it has these big jumps in it and the original data didn't. So the null hypothesis basically says that your shuffled data looks just like the original data. The shuffled data is just as likely to happen as the original, and circular shifting doesn't work for that. I'm going to talk about something later, which is linear shifting, and that does work. It doesn't have the problem. All right, any other questions? All right, so next, so there's a subtle distinction that only very, very late from our very own, well, the UK's own Chin Yuan Zhao in Cambridge wrote this amazing paper that 100 years too late really identified what's the difference between two very related things, a randomization test, which we talked about before, and the permutation test. So a randomization test needs a randomized experiment, but you don't always do a randomized experiment. Suppose you're trying to relate the recording of some neurons to the behavior of the mouse, right? The mouse chooses right or left, it's their decision. The neurons fire or not, that's their decision. You didn't randomize anything. So you can't do a randomization test. A permutation test doesn't require a randomized experiment. Instead, it tests that the probability distribution of the outcome is invariant under permutations. It's almost the same, but without requiring a randomization. So let's now consider this case that we've got, instead of a block variable that we control, so we can re-randomize it and do the randomization or pseudo session method. Let's suppose that we didn't have anything random and we want to ask, is the firing of the neurons correlated with the decision that the mouse made, right? We can't use a pseudo session test because we don't know how to regenerate either of those. We don't know how to regenerate the neural activity because we don't have a probability distribution for that. And we don't know how to regenerate the behavior because we don't have a probability distribution for that. So instead we use a permutation test, and this one is called the session permutation method. So our data again is, and the difference with this one, the previous one, the pseudo session, only needed one experiment. It only needed one session to get a p-value. This one though, you need to have several sessions to get a p-value. So let's suppose we have big S sessions, and we call the firing history of the neurons XS, and the history of the stimuli, we call that YS. Sorry, the history of the choices that the mouse made, we call that YS. And we want to test the null hypothesis as before, that the whole history of stimuli, the whole history of neurons is independent of the whole history of choices that the mouse made. We can't use the pseudo session or randomization test. This is another way of doing it. So what we do is we ask, can you predict Y from X? Can you predict the behavior from the neurons better when they come in the same session than if they came in different sessions, right? So if there really is a correlation, you ought to be able to predict the behavior on session 1, the choices on session 1 from the neurons on session 1, better than you can predict the choices on session 2 from the neurons on session 1. So this is what the session permutation method does. You define all the permutations of S objects. You've got S sessions. There are S factorial different permutations of them, where you assign the choices on session 1 to session 3, session 2 to session 5, etc. And you loop over all those different permutations, and you define a test statistic now for the whole set of sessions, right? So for every session, you ask, how well can I predict the choices from the neural activity? That gives you one number per session. You add it up over sessions. That gives you the test statistic. And now you compare that actual test statistic to the null distribution you get by shuffling the sessions, right? So let's look at an example. So here we've got 5 sessions that were like we saw before. This is the case that there's no encoding of the block variable or the behavioral choices in the neural activity. You can predict the mouse's behavior from the activity of the neurons because there's a nonsense correlation, but you can't predict it any better than you can predict the behavior on another session because they're actually independent of each other. So if we apply this then to the case where there's no correlation, then we find that the actual test statistic is right in the middle of the null distribution, because you might as well have permuted all of the sessions and predicted the wrong session's choices from every session's behavior, and that'll work just as well because it's only a nonsense correlation. On the other hand, if you have an encoding of the block, then you can predict the actual session better than you can predict the shuffled sessions. All right, so that's the session permutation method. You can use this when you've got slowly drifting neural recordings and correlated behaviors from one trial to the next. They'll always be correlated, but when you don't have a randomized experiment, something else you can do. For example, if you're predicting choices from neural activity when neither of them was randomized. All right, so for the session permutation to work, you really need at least 5 sessions, because the p-value you can get is at least 1 over the factorial of the number of sessions. So if you've got 4 sessions, 4 factorial is 24, maybe you can get p equals 0.05, but you really want 5 sessions so you can get p less than 0.01. If you want to do a session permutation test, you really need 5 sessions. You don't need to record the same neurons each time, right? If you record a different set of neurons on session 2 than on session 1, it doesn't matter, because you're still asking, can I predict the behavior of the actual session better from the neurons on that session than another one? It doesn't require stationarity. We'll get to what that means in a moment. It does rely on Y to be different between sessions. So if you're going to ask, can I predict the behavior on the correct session better than another session, then they better make different behavioral choices on the different sessions, right? They better have different sequences of behavioral choices on the different sessions. And it doesn't show causality, it just shows a correlation, right? So if you've got something that affects these two sequences together, then you could get a correlation. It'll be a genuine correlation, but not causal. So for example, let's suppose you're recording in the motor cortex and your electrode was destroying the motor cortex. Then you'd see a degradation in performance, and you'd see also a degradation in recording quality. So you might find a correlation between the neurons and the behavior just because of that variable. So you've got to be careful about that. As always, a correlation doesn't prove a causation. And it's probably best for the sessions all to come from one subject, because otherwise you might find that some subjects you record more neurons and others less, and they also have different behaviors. Yes?
What applies to tasks where the behavior is like very stereotyped?
Yeah.
And it's not necessarily like it's like very different why.
Exactly. If the mouse made the same sequence of choices on all of your trials, then you can't do it. There's literally no way you can ask if neural activity is correlated with those choices. You've got to have some sort of a task that they respond differently to on different sessions. And there are ways to do that, but this is exactly the sort of reason that you've got to think about these things even when you're designing the experiments, right? So if you have blocks like we do here, and you can randomize those, that's the best. If you don't, you can do things like randomizing the rewards. Rather than always giving a reward for correct, you give a high chance of reward, but occasionally don't give a reward. All right. Okay, next is the linear shift method, which is what we talked about earlier, right? So we've had two approaches so far. One is the pseudo session method. That's when you have a randomized experiment. It doesn't need to be independently random on every trial, but it needs to be random within a session. You have a random sequence of stimuli or rewards or something that you can then regenerate. We've had the pseudo session method that doesn't need that, but needs multiple sessions. If you've only got one session and you don't have something random that you can regenerate, you need to make another assumption. All right, so now we define stationarity. So a random process, remember, is a probability distribution for sequences, and it's called stationary if you can shift the sequence in time, backwards or forwards, and the probability distribution stays the same. That's a property of the ensemble or of the probability distribution. It's not a property of any one instance. If you look at the data for one session, you can't tell if it's stationary. You need to look at the ensemble. So here's an example. Each of these animations shows a block sequence. One of them is stationary and one of them is not. Anyone want to tell me which is which? Which one is not stationary? The one on the left is not stationary. I'm assuming that's what you pointed to, but I couldn't triangulate. The one on the left is not stationary, right? The reason the one on the left is not stationary is if you look at child 0, it always starts at 0, right? The one on the right sometimes starts at 0, sometimes starts at 1. If it always starts at 0, then it's not invariant to these shifts, right? Because it means that at 0, we've always got a 0, but at 200, sometimes we've got a 0, sometimes we've got a 1. So it's not invariant to the shift. So it's not stationary, the one on the left. The one on the right is stationary. It's not about anything else. You can have like explosions and then it goes quiet and then it explodes. If it doesn't do that at a predictable time, it's still stationary. The point about stationary is there's no predictable times. All right, so the test we're going to come up with it assumes stationarity. So we've got our neurons, which we'll call X, and let's say the behavior of choice that we'll call Y. And the way this shift method works is that you take a chunk of data from the middle of the sequence and you shift it along the other one. So we take a chunk of the neural activity from the middle of the sequence and we ask, and we compute its correlation with the corresponding time points of the behavioral choice. So we predict the behavior from the neurons for this chunk of data in the middle of the recording. And that gives us our test statistic. And then we compare that to a null ensemble that we get by shifting this block of neural activity from the beginning through the middle to the end of this sequence. And that gives us all sorts of different predictions of the behavior at the wrong time, right? So the null hypothesis is that you predict the behavior at the correct time better than you predict the behavior at the wrong time. And there's a bit of a twist in the math, which means that normally what you would do is if you've got the number of shifts from minus n to plus n, then you've got 2n plus 1 different shifts. You'd normally reject the null at p equals alpha if the actual test statistic is in the top alpha fraction of these 2n plus 1 shifts. It turns out for it to be strictly valid, you need to reject it if it's in the top alpha n plus 1. The reason for that is that you can come up with an absolutely absurd counterexample where you can get a false positive result if you use this p-value. The details are in here. It would require a mouse whose strategy in the task is not to gain the maximum reward possible, but whose strategy is to screw up the experimental statistical analysis. But if you really want it to be sure it's not going to happen, you can use this more conservative p-value, and then you've got a statistical test that works here. So what you do, just to say it again, you've got your sequence of neural recordings, you've got your sequence of behaviors, you take a chunk in the middle by throwing away n trials at the start and end of your neural recording. You predict the behavior from the neural activity contemporaneously, and then you compare the prediction of the actual same time points to the prediction of a shift of the behavioral variables at the beginning and all points in between to the end. So you get 2n plus 1 of these shifts, and that gives you the null ensemble. You're asking, can you predict the actual same time points of the behavior better than you can the ones shifted forward and backward in time? And this is like the circular correlation, but it doesn't have that problem that you get this discontinuity, and you can actually prove that this is a valid test, which you can't for the circular correlation because it isn't. All right, so here's an example. We've got now just binary time series. This is a case where they're not correlated with each other. They've got a serial correlation, right? They've got these static bits and they flip up and down, but they're not correlated with each other. And this shows you that the test statistic, how well you can predict y from x, as a function of the time shift. And you see that this one peaks at around -5 and then at -20. There's nothing special about 0. But this one, where they actually are correlated, has a peak at 0, right? You've got the autocorrelogram between the two of them, shows how well you can predict y from x as a function of how much you're shifting x. And it has a peak at 0, which means that there's a genuine correlation between them rather than just a nonsense correlation. So this is another way to avoid the nonsense correlation. It doesn't require randomization. It doesn't require multiple sessions, but it does require this assumption of stationarity, which means that if you've got something funny going on at the beginning of the experiment, it's not going to work. So you need not to have a case where the mouse starts off really hyper and is going to do great at the task, but also has a higher firing rate. So that's the caution with this one. All right. How am I doing for time? Running out. Okay. Power through this. All right. So now a couple of quick ones. So The pseudo-session method tests if the whole stimulus history is independent of the whole behavioral history. Sometimes that's too strong of an assumption, right? And for example, we'll see a case where the mouse makes a choice and it may or may not get a reward, right? And you could say it didn't see the stimulus, but it sure as hell knew about the reward, right? So if you're testing the hypothesis that the entire sequence of choices is independent of the whole sequence of stimuli, and the reward depends on the stimulus, and the mouse can see the reward, then the sequence of stimuli is not independent of the sequence of choices. All right, but what you can do often is phrase the null as a distribution for the observed variables conditional on some reduction of the data and do a randomization test based on that. Let me give an example. So this is the example from Andy's work, where the mouse is sitting here in front of a screen, a stimulus comes on, and the mouse simply has to turn a wheel to respond to the stimulus and then to get a reward. And luckily for us, Andy thought to randomize the intertrial interval and the length of the quiescent period. So the mouse, to avoid it just turning the wheel all the time, the mouse has to keep the wheel still for this quiescent period before the stimulus appears on the screen. And the intertrial interval and then the length of the quiescent period are both random. Now the stimulus appears and they turn the wheel to get the reward. So even though even if the mouse couldn't see the stimulus, we want to test, can the mouse see the stimulus? Can the mouse respond to the stimulus? Even if the mouse can't see the stimulus has an effect on the reward, and the mouse can certainly detect the reward. So you can imagine a mouse doing a strategy of just waiting a bit after the last reward to turn the wheel. And if that didn't work, wait a bit longer and turn it again. So the mouse is going to respond to the apparently respond to the stimulus, even though it can't see the stimulus. So the conditional randomization test works like this. You have the sequence of, I call them here button presses, but they're really wheel turns in this case, that come at different times. And on every trial, there's the time the actual stimulus came on, and then there's a range of periods that it could have come on, right? So the quiescent interval is chosen at random on each trial, and you know that the actual stimulus had to be sometime between the end of the quiescent period and the time of the reward. So your null hypothesis is that it could have come at any moment in this range. And what you see here is three examples, two of which are cases where the mouse can't see the stimulus. So here, we've got the mouse just pressing, turning the wheel completely at random times. And the green is the feasible range where we resample the stimulus from, and the red is the actual stimulus. This is the histogram of reaction times of the mouse. So the red is the actual reaction time, and the blue is what we get when we redraw the quiescent periods from this probability distribution, the conditional distribution. And you see that the actual reaction time, when the mouse just turns the wheel at random, is right in the middle of the null distribution. So we don't reject the null hypothesis, which is good. Here, we have a case where the mouse actually does respond to the stimulus, and you can see that the reaction time is shorter than the null distribution, which is also good. Here we've got this funny case where the mouse turns the wheel without looking at the stimulus, and it keeps turning it ever a bit more slowly until eventually it's waited longer than the quiescent period, which it didn't know, but just happened to get by chance, until it gets a reward. And you can see that the reaction time here is actually faster than it is if the mouse responds to the stimuli with a bit of a delay. Nevertheless, it's still not a significant answer. So what this test has done is it's, even though the behavioral, the whole sequence of behaviors is not independent of the whole sequence of stimuli, it was able to reject the null only when the mouse really can see the stimulus. Oh, and here's the actual data. So we use this to show that it takes the mice about 3 or 4 days before they start actually responding to the stimuli. Their reaction time is getting shorter over the first few days. Nevertheless, that doesn't mean that they're learning to see the stimuli, right? So the reaction time's getting shorter, but they're still not seeing the stimuli. They're just turning the wheel ever faster. And it's only on about day 4 and on that they learn to actually respond to the stimuli, because that's when the measured reaction time keeps going down, but the null distribution here has plateaued. Okay, the last one, and because I'm basically out of time, I'm going to skip the math of this, of which there's a lot. Okay. Yeah. Okay, so this is for the International Brain Lab task. So the International Brain Lab, it was this behavioral task where the mice, again, sit in front of this wheel. A stimulus appears on the left or the right. There's a block like we had before. The block keeps switching from left blocks to right blocks. And when it's in a left block, there's an 80% chance of the stimulus on the left. And when it's in a right block, there's an 80% chance of the stimulus on the right. And we want to ask, can the mouse see the stimulus, right? And the thing is that the mouse, even if the mouse can't see the stimulus, they'll be able to get some reward in the task by doing a two-arm bandit strategy, right? So if they just blindly choose left or right, if they're getting rewards on the left, that means the stimulus is more likely to be on the left, which means it's probably in a left block. So a strategy where they just win, stay, lose, switch is going to get them some more rewards than chance. If we want to test whether the mouse can actually see the stimulus, what we can do is this thing called the Martingale Z-test. And because I ran out of time, I'm not going to tell you about the math about it, but I'll just tell you the easy way to do it. And that's called tangent sequence randomization. So a tangent sequence is one where you resample every trial conditional on the history up until then, right? So in the pseudo session method, we resample the entire history, but in the tangent method, you only resample every trial given what happened before. And that gives you another way of shuffling, and without going into the math too much, that is still valid, but now only approximately so, and it works on in many situations, but not quite every situation, and I can talk about that later. But again, the point is that this method, you don't need to resample the entire sequence. You just resample the stimulus on every trial, conditional on what happened before, and it normally will give you a valid test. Okay, so I've run out of time, so I'll finish. So to summarize, traditional statistical methods don't work for correlated time series. You've got various options of what you can do that's valid. And of course, you also have the option of not doing a valid statistical test, and that might help you publish your paper in a luxury journal. And whether you choose to do that or not is between you and whatever higher power you feel like invoking. But all I can do is beg you to use a valid statistical test, even if it counts against the interests dictated by our flawed, yet no one can seem to think of a better system of incentives for scientists. All right, so traditional methods don't work for correlated time series. The neurons are always correlated, the time points are always correlated. If you know the probability of one of the time series because you randomized the stimulus sequence or something like that, use a pseudo-session method, the randomization test. This is almost foolproof. If you have multiple sessions, ideally of the same subject, use the session permutation method. If one of the stimuli sequences is approximately stationary, use a linear shift method, not the circular shift method. Use conditional randomization if you can phrase your null hypothesis as a conditional distribution, like in that reaction time task. Use the martingale z-test if you, I haven't defined martingale because I ran out of time, but if you can talk about the probability of one trial given the history up until that moment, which you often can, then you can use the martingale z-test or the tangent sequence randomization. And the most important thing is before you even start your experiments, make sure you randomize everything that's not nailed down, because then it'll give you options to do these statistical tests later. If in doubt, randomize everything. And that's it. Thank you very much. Yeah.
In terms of the session permutation test, we thought about whether it is possible to permutate the neurons instead of the behavior. Because in most cases, the neurons should be high dimensional compared to the behavioral variable, and you have more flexibility. Say, if you have 3 sessions and you are trying to permutate on session 2, you can grab half the neuron from session 1 and half the neuron from session 3 to do the prediction.
Yeah, no, I wouldn't do that. So the thing is, you need to keep everything in one session together, right? So your session permutation is going to be something like this, that you take the neurons, all of the neurons from session 1, and you use them to predict all of the trials on session 3. If you split the neurons across trials, what you're doing is you're assuming a null hypothesis that the neurons are independent of each other, right? Because even if your test statistic didn't involve the behavior at all, it just involved the correlation of different neurons. When you start to split and swap neurons between sessions, you're adding to your null hypothesis the assumption that the neurons are independent of each other, and that's really not going to be true. So you're getting a statistically significant result, but only because you assumed a null distribution that's ridiculous. So I wouldn't do that. Yes.
So if I understand correctly, you said that in the pseudo-session method, you require that the history of the behavior, the history of the stimulus are independent.
Yeah.
But usually when animals behave, they have some sort of response that changes across the session.
Yes.
For example, after one correct trial, there is a higher chance of another correct trial.
Yes.
Than if an error occurred previously.
Yes.
So how many tasks do you think it actually you can really say that these time series are?
Yeah. Okay, so that's a great question. And the point is, it's when you've got something like a stimulus sequence that you might as well have simulated before the experiment starts and then just fix it, right? So in the case that the stimulus on trial N depends on the history up until trial N, you can't do this because then, you know, the stimulus depends on the mouse's previous choice. So by definition, the sequences aren't independent. But if the stimulus on trial N doesn't depend on the mouse's behavior up until trial N, then you don't have this problem, right? So if you do things like baiting on incorrect, you can't use it. But if you have the stimuli that you might as well have pre-generated before the experiment even started, then you can use it. The case when you've got baiting on incorrect, that's when you'd use the martingale z-test. That's when the stimulus does depend on the history up until that point, but you can still pick it from a probability distribution in each trial, conditional on what happened before, right? And so it's not as good of a test because it's not provably always correct, but it's provably usually correct. And that's this tangent randomization where you repick the stimulus on every trial, conditional on the history up until that point. Did that answer the question? Okay. Yes.
Thanks for this really. I'm just wondering, like, in the summer slide, you have this list of scenarios where, like, in which case you should apply which test. I'm wondering if there's like a systematic way of testing whether these like assumptions is set aside. For instance, in the stationary case, is there anything that we can do to say, like, we set aside this constraint and then that's why we should apply?
Yeah, okay, so that's a good point. So the assumption for the pseudo session method, that one's easy to know, right? Because basically you can use the pseudo session method if the stimulus sequence is something that you might as well have simulated before the experiment started, because it doesn't depend on anything that happened during the test. And this is always the best one to use if you can. The session permutation method, you're pretty safe with that one, unless you've got something like this, slow destruction of the neurons that correlates with a worsening of behavior. For linear shift, this is a more difficult one because it's usually not stationary, because it usually is the case that when you put a mouse in a rig, they really want to get the reward and they're really working hard. And by the end of the experiment, they're not working so hard. And also you'll probably have the neurons less active. And so then you do have to worry a bit more about that. And I think the way to do this, I don't think there's any formal rule, but if you just look at the behavioral trace and you see that that it's fairly constant throughout the experiment, you're not getting to the part at the end where they're just not bothering. Or if you do get to that part, you cut it out and you don't do the statistical analysis on that part, then you're probably okay with a linear shift. If you can't see anything with your eyes, there's a degradation in performance over the history of the experiment, then you're probably okay with linear shift, but it's not as rigorous as the others. The last two, the math is a bit more complicated, but these two, it's a matter of, can you prove it works, right? So for conditional randomization, if you can prove it works, then it works. For martingale z-test, it normally works if you've got enough trials. How you know you've got enough, I don't know. It's sort of the same is true of t-tests, that you need to have enough trials if you don't have a Gaussian distribution. So it's probably okay, this last one. But the most important thing is to do a randomized experiment so you can use the pseudo session method. All right, yes?
When we do the conditional randomization, the answer sometimes depends on the statistic. So, for example, if we use the median reaction time, we get an answer that is slightly different than the median reaction time. Do you have an intuition for what that is?
Yeah, I mean, I think that always happens with any statistical test, right? So you've got your shuffling method and your test statistic, right? And what a statistical test isn't supposed to do is give you significance at p equals 0.05 more than 5% of the time if the null is true. That's all it's supposed to do. it's okay. This test is still valid if it never rejects the null hypothesis at all. It would still be a valid test. So they don't have to give the same answer. You can have two tests that are both valid, but they give different answers. But if they're valid, then neither of them is giving you a false positive more than 5% of the time. I think it's just that.
Yeah, so it's just, I don't know why, but so when we use the mean, I think based on activity and other things, we're getting a correct rejection of the null more often than if we use the median.
I don't think we should have been getting an incorrect rejection more than 5% of the time.
I don't know why, but there is a difference. And by I think the mean works better than the median. Because it's giving you more correct rejections, the mean? Yes.
Well, then that's absolutely possible, right? Some test statistics are more powerful than other ones, and the mean could be more powerful than the median, which means it's giving you more correct rejections. The median is still a valid test because it's still not giving you very many incorrect rejections, but it's just not giving you as many correct rejections. So in any test like this, the validity comes from the shuffling method, and the power comes from the test statistic. And it's the shuffling method that's described here, right? So this is all about the shuffling method. It doesn't say what test statistic to use. If you use the right shuffling method, you shouldn't have a rejection at more than 0.05 probability if the null is true. But the number of times you get a correct rejection, it could be that you never get a correct rejection if you use a stupid test statistic. Or it could be that you always get one if you use a very good test statistic. And so I think that there is a difference between the mean and the median, is that the mean was a better choice of test statistic. Oh, yeah.
I have a question about a slightly different experiment where, say, you have a population of neurons and you want to compare them to a population of neurons recorded at the same time. I guess any spurious correlations will be happening for both populations. So in that sense, I guess are more traditional statistical tests valid if you're kind of comparing population A and population B with each other?
Ah, right. You want to say, is population A more correlated to behavior than population B? That is a difficult one. There is a way, and I didn't talk about it, to do a partial correlation version of the session permutation test. So you're saying, can I predict the behavior any better if I have access to population A and B than population A alone? That's not quite what you asked, but it's a bit similar. There is a way to do that. I didn't talk about it today. Another preprint, have another preprint on it with Alex Yuan. But what you actually asked, I don't know how to do that. I mean, it's a great question. I just don't know how to do it. Yes.
It was very interesting, and this is a very interesting, not very heavy person. You refer to multiple groupings, but is it one case where us were biologically trained people read on this?
Well, I hope this first one, I should have put the titles. This one is just called Nonsense Correlations in Neuroscience. It doesn't cover everything. It covers the first three, but those are the most important. I need to update it. I need to update this so it includes all of them, and I need to send it to a journal. But you know, there's always something else to do.
Okay, could you give one advice to, again, that we'd like to do this correct, we just have not enough intuition for these things.
Design a randomized experiment, right? Randomize everything that's not nailed down. Randomize your stimuli, randomize the rewards, randomize the time intervals, all of these things, and then you can do the pseudo session method, right? The pseudo session method, I hope you got that one, because there wasn't so much math involved there. You just regenerate whatever it was you randomized, exactly like you would have done in the original experiment. And if the actual sequence gives you a better correlation than the randomized one, then you've got a significant result. So that's what I'd say, and it's almost foolproof, this pseudo session method. The way you get a mistake is if you have a bug in your program, but you shouldn't get, because you made some assumption that's incorrect, because you know how you regenerated, you know how you generated it originally, so you know how to regenerate it. All right.
I think we'll leave it there. Thanks so much.
Thank you.